We move to the last topic of the course, durability, the most challenging one, and we start by studying the effect of temperature and water. So we have concluded the joint design part. Now let's move to durability. Durability is a big issue. It's rather simple to design the joint for the short term, and we have seen this basically in the joint design part, but to design for the long term, taking into account water, temperature, fatigue, creep, that's much more challenging, and that's the subject of the last two modules on durability. The first one, I will talk about hygrothermal aging and temperature. About temperature, if you talk about metals, for example, you have problems of corrosion, but this is a surface problem. In the case of adhesives, which are polymers, it's not. The water will diffuse inside the material up to the core if you let it. And the water can go in, it can go into the spaces, and there are plenty between the molecules, or connect to the molecules, we call it bound water. Anyway, to measure the rate of diffusion of the water inside the adhesive, we do weight measurements. We put a sample into water and we we measure the weight at regular intervals. And then we plot the result in a graph where we have weight gain versus square of time. And this line typically will appear. It can have several stages. It can have a plateau or not, but it's more or less like this. And from this line you can deduce D, which is the coefficient of diffusion. With this coefficient, you know how much or how fast the water will ingress into the adhesive. It's important also to know how fast the water will go out of the adhesive when you dry the sample, because typically in reality we'll have cycles where there is high humidity and then the humidity goes down and you have drying of the adhesive. So it's important also to measure the water desorption. And depending on the fluid the adhesive is in contact with, the desorption can be abrupt or not. Take for example the case of distilled water. This is the period of absorption, and then when you dry, you basically remove all the water that is inside the adhesive. But take the case for example of salt water. First of all, the amount of water is not comparable. The adhesive will absorb much less water, and then the desorption also will not be as much as when you have distilled water. This is basically due to the presence of salt. The salt will not let the water go in because it will be like a barrier, and it will not also let the water go out because it's another barrier. So this desorption problem is also important to measure. Also, when you have several cycles of absorption, desorption, the coefficient of diffusion is not constant. Between the first and the second and third, it will be different. After, it tends to stabilize, but it's important also to measure and to know what is the coefficient of diffusion for the various cycles. Okay, now what's the impact of the presence of water in the adhesive properties? That's depicted here in this graph where you have stress versus strain. And this is for the virgin adhesive, there is no water, and as the amount of water increases, the strength will decrease and the ductility will increase, which is not a very bad thing if you think about the effect of ductility in the joint strength. We have seen this in the joint strength or joint design modules. The problem is when you have chemical change in the adhesive due to the presence of water, which is when you have hydrolysis. When you have hydrolysis, you have a breakdown of the molecules, and this is not possible to recover the properties of the adhesive. We are talking about chemical aging. You have to distinguish between physical aging and chemical aging. Physical aging, you can recover the adhesive properties. If you go up to this point where you don't have hydrolysis and you dry the adhesive, then you go up to the beginning. This is physical aging. If you pass that limit and you have hydrolysis, if you dry the adhesive, you don't go back. There is permanent damage in the adhesive. Chemical aging causes permanent damage, and we are talking about hydrolysis. You have more things important that take place when you have water. You have chemical changes actually, especially at the interface. The interface really is the nightmare thing of adhesive joints. If we look in detail at what happens at the interface, take for example the case where you have an epoxy that cures with an amine, then first of all the amine will tend to concentrate and go to the interface. Second, the metal oxide, when you use metals, will tend to be dissolved in the adhesive. And third, you might have a chemical reaction between the amine and the metal oxide. So really, here, close to the interface, we are talking about a different chemistry from the rest of the material. You have to take that into account if you want to have a proper joint design. Another thing that typically occurs when you have the joint in contact with water is that the coefficient of diffusion at the interface is much faster. You have a concentration of water at the interface, and this might cause osmotic pressure due to the variation of water concentration and cause eventually interfacial failure. So as you can see, one thing is the effect of water in the bulk adhesive material. Another thing is the effect of water at the interface. It's two completely different things, and it's much worse at the interface. The presence of water in the adhesive will cause swelling. The volume of the adhesive will increase. When it's free to increase, no problem. But when it's in a joint, it's not free to increase. So this will cause residual stresses. You will have residual stresses due to the swelling of the adhesive. And of course, more at the ends of the overlap, which will add to the mechanical loading. Be careful with that. We have here a slide which gives you a global approach, how you can treat this. And you have to distinguish between what happens in the bulk of the adhesive, in the middle of the adhesive, and what happens close to the interface. First thing to know is how fast the water will ingress into the adhesive, okay? And how or what will be the impact of that water in the adhesive. Okay, this is nice and quite easy to do for the adhesive. For the interface, it's much more complicated. You know how fast it goes in. This is not too complicated, but to know the interface properties is extremely difficult. But let's assume you can do it. Then you do a coupled numerical model, diffusion mechanical, and when you or when the stress level reaches the failure strength of the adhesive, it fails. Or when the stress level reaches the failure strength of the interface, it fails. Of course, this is theory, but in practice, very difficult to implement, especially because of that. Another thing you can have, and that is not contemplated here, is corrosion of the metal when you use metals. About the temperature, we have already discussed this when we talked about the mechanical characterization of the adhesive, but you know that the strength will decrease and the ductility will increase. This is not a bad thing. Again, the problem is when you are above TG, so be careful and make sure you are not above TG. One thing that the water does, by the way, is to decrease the TG. So when it's full of water, the TG of the adhesive will be much smaller, and you think you are below TG, but actually you might be above TG. So be careful with this, and you should know also the effect of water on the TG of the adhesive. And we have already discussed this, but I stress this because this is very important. When temperature is involved and when you use dissimilar materials, because of the difference in coefficient of thermal expansion, you have residual stresses in the adhesive, and this will add to the mechanical stresses and might cause a premature failure of the adhesive. So that's for the first part of the durability, the effect of water and the effect of temperature.